The mean value theorem, another application of the derivative, which states that if a function is continuous and differentiable over an entire interval, on that interval, it is going to have the derivative that equals the average rate of change at least once. But before we get to the mean value theorem, let's talk about Rolle's theorem, which basically says that if a function starts and ends at the same place and it's continuous, then it's got to have a critical number somewhere on the interval. So in a nutshell, Rolle's theorem says that if a function has the same function value, the same output at points A and B, and it's continuous over an interval, then the function's going to have at least one critical number on the interval. So the first condition is that f of A has to equal f of B. So we've got this interval AB, and we're going to just look at this interval. Rolle's theorem is only true over a certain interval, and the function has to have the same value at A as it does at B. The y values are equal at A and B. If it starts and ends in the same place on the interval, and another way of saying that is that f of A equals f of B, and the function's continuous, it doesn't have any breaks, such as this pink function here over the interval, then the function has to have a critical number over the interval. It's going to have at least one place where the derivative equals 0, a critical number, a minimum or a maximum. Now, it could be a local minimum or a maximum, as is the case with this function, but indeed, it's got to have that critical number somewhere at least once. And in fact, this function has, it looks like, at least possibly 3 to 4. One here, and one down here, and possibly one just past A and one just before B. So it can have at least one. It can have many critical numbers, but it must have, according to Rolle's theorem, at least one. And if you were to try to create a function between A and B that starts and ends at the same place, you would be hard-pressed to create something that has no places where the slope equals 0. No matter what you were to draw, you're always going to at least have one place where the slope equals 0. In fact, what we would call the degenerate case would be the case where the function is flatlined over the interval. And you might say, well, it doesn't have a critical number. It doesn't have a minimum or a maximum. Well, indeed, the slope is 0 throughout. So the entire interval, in this case, has critical numbers. So there is no way you can create a function that's continuous over this interval that doesn't have at least one and perhaps many critical numbers, places where the derivative equals 0. So let's do a Rolle's theorem example. And we're going to look at the function f of x equals 1/2 times the quantity x minus 3 squared plus 2. Quadratic, second degree polynomial. So question number 1 is, does Rolle's theorem apply over the interval from x equals 1 to x equals 5? So the first question is, does f of 1 equal f of 5? And indeed, f of 1 equals 4, f of 5 equals 4. So that part of the theorem applies. Also, it's a polynomial function. It's not a rational function. It's not a radical function. Therefore, it's going to be continuous. So it's continuous, and f of A equals f of B. Therefore, the answer to question 1 is yes, Rolle's theorem does apply for those reasons. So the second question is, since it does apply, what must occur over the interval? Well, Rolle's theorem tells us that if those conditions are true, somewhere over this interval from 1 to 5, we're going to reach a maximum or a minimum. We're going to have a critical number. Since this is a parabolic function and its coefficient is positive, we know it's an upward-facing parabola. That means that this critical number is going to be a minimum. And indeed, when we graph that, and we look at this interval from x equals 1 to x equals 5, we see, lo and behold, that since we begin and end at the same value, Rolle's theorem applies and does tell us that minimum has to occur. And in fact, this minimum occurs at x equals 3. Now let's get into the mean value theorem that says that over an interval, if it's continuous and differentiable, there's got to be at least one place where the slope of the tangent line, the instantaneous rate of change, equals the slope of the secant line, the average rate of change. The mean value theorem is a little bit more complex to comprehend than Rolle's theorem, but it's also much more valuable because you'll recall that Rolle's theorem requires that the functions start and end at the same place, and that's pretty rare. Mean value theorem does not have such restrictions. The requirements are that the function be continuous and differentiable. So as long as the function is continuous and differentiable, and usually if it's continuous, it's also differentiable over an interval, then there's going to be at least one point on that interval where what we call the instantaneous rate of change, or the slope of the tangent line, is equal to the average rate of change over the entire interval. So let's look at some interval a to b. And so we have an f of a and we have an f of b on this interval. And between them is a function, and it can be a pretty complex function. Note, we do not have to have the same starting and ending value like we do on Rolle's theorem. So let's first build the secant line, the average rate of change. And we don't really need calculus to do this, and really without calculus, this would probably be the best we could ever do in finding rates of change, is to just get as small an interval as we could and try and find the average. Of course, calculus allows us to do much more than that. But for the mean value theorem, we have to know what the average rate of change is over the entire interval. And you'll recall the slope of this is f of b minus f of a over b minus a. Very much y2 minus y1 over x2 minus x1. The average amount that this function is changing over the interval. And you can see intuitively in this case, the function is rising slightly over the interval, so it's slightly positive rate of change on the average. But that by no means is that the instantaneous rate throughout. You can see it's going up and down and changing constantly throughout. Here's where the mean value theorem comes in. It says that there's got to be at least one point on this interval, and this point I've chosen C is a pretty good one. At this point, C comma f of C, there's got to be at least one point where the slope of the tangent line, that's denoted by this red segment here, the slope of this tangent segment is equal to the slope of the secant line. This point at C, this is an instantaneous rate of change. Using calculus, we can find that if we know this function. We can find at that instant C, what is its slope? And the mean value theorem guarantees there's at least one place in this function where this slope of the red instantaneous rate of change, this red tangent line, has to equal the slope of the secant line. And in fact, it probably occurs at several other points on this function because this function is changing so rapidly. You can probably see somewhere around here, you'd have a similar kind of situation. Maybe even somewhere around here and here and here. Several places on this function where this might occur, but the mean value theorem guarantees that it's going to happen at least once. So let's look at an algebraic example of the mean value theorem. Let's consider the function f of x equals the quantity x minus 3 squared minus 2. Parabola, second degree function. Question number 1, does the mean value theorem apply over the interval from 1 to 6? If it does, what does it tell you must occur? And then where does this occur? So let's take this one step at a time. Let's look at the function on the interval from 1 to 6. Mean value theorem requires that over this interval it be continuous. It is. And it be differentiable. It is. So what does the mean value theorem tell you must occur? Well, it tells you that the slope of the secant line, which is the average rate of change over the interval from 1 to 6, has to be equal to the slope of the tangent line, the instantaneous rate of change, somewhere on this interval. And intuitively, we can kind of see this is a pretty fast rate of change, and it's positive. It ought to be somewhere in here, intuitively. We're going to find out where this occurred. Well, the mean value theorem says it's somewhere on that function, which equals 1 and x equals 6, that instantaneous rate of change has to equal the average rate of change. Well, we know the average rate of change. We can find that without calculus through f of b minus f of a over b minus a. So if we crunch the numbers here and find the slope of that secant line, we get f of 6 minus f of 1 over 6 minus 1, which is 7 minus 2 over 6 minus 1, 5 over 5, positive 1. The slope of the secant line over that interval is 1. So somewhere along that interval, the slope of the tangent line at some instant is also got to be 1. And intuitively, we think it's somewhere down here, visually. Analytically, we're trying to find out where f prime of x, the instantaneous rate of change over the entire function, what instant that equals 1. So if we're going to set f prime of x equal to 1, well, let's take the derivative of that function. And if we use the chain rule on this to find the derivative, it becomes 2 times the quantity x minus 3 to the first power times the derivative of what's inside, which is just 1. Derivative of 2 is just 0. So the derivative of this function is 2 times the quantity x minus 3. We're going to set that equal to 1, find out where that occurred. So algebraically, we're going to set that derivative equal to 1 and solve for x. 1 equals 2 times the quantity x minus 3. A couple of ways to do this algebraically. I'm just going to divide by 2 to get 1/2 equals x minus 3, and then add 3 to both sides, so x equals 3 plus 1/2, or 3.5. So at that point, which algebraically is 3.5, it's actually negative 1.775, but GeoGebra's rounding this. At that point, the tangent line slope is also equal to 1, and you can visually see that. We've drawn the tangent line, we've drawn the secant line, you can see their slopes are identical. That only occurs once on this particular interval, but it could occur more than once in some situations. So we've talked about the mean value theorem, the idea that on an interval, if it's continuous and differentiable, the slope of the tangent line is equal to the slope of the secant line, at least at one point.